Okay, everyone, thanks for coming here and in the recording. Today we're going to have Ethan Torres speak, who is now a postdoc at CERN, and I want to put it on record. He's also the person who cleaned up at Strings Trivia Night in 2023. So we'll see how he does when he's on home turf in 2024. So,
Yeah,
okay.
yeah. I mean, if I feel like a postdoc competing might not be fair because I was competing with a lot of grad students, but anyway. Thanks for the nice introduction. Okay, let me share screen. Wait just a second. Let me just make sure I have too many PowerPoints up is the problem. Hold on just a second. Yeah, sorry, it's just the PowerPoint for the talk isn't showing up. It's on like my PowerPoint, but it's not showing up as something I could share
Yeah, no problem.
screen. I guess I can just share my entire screen. I guess that would also be okay, but usually that's yeah, I guess I'll just share my entire screen then. There's issues with that. And then slideshow. Okay, great.
Yep.
Okay, yeah. So today I'm going to tell you about symmetry operators from Branes. Um, this is a topic that is lies in the intersection of string theory and quantum field theory, and in particular informs this recent activity of generalized and categorical symmetries in quantum field theory, and um, has string theory kind of saying new things in this arena. So just a basic, oh, I'm sorry, this thing's in the way. It's just a basic outline. So first I'll highlight kind of the main idea of how you can map string objects to symmetry operators, and also string-like objects to defects charged under symmetry operators. And I'll go through a very easy example of just the 70 Superang-Mills theory, and then also discuss how continuous symmetry operators can be incorporated into this framework. And then we'll see one application where we couple a quantum field theory to gravity, and see how we might have global symmetries emerge in the infrared limit. And also discuss an application to frozen singularities in M theory, which is a work in progress. Okay, so okay, why is it? Okay, okay, good. So the general idea is to take. Can you all see my cursor, by the way? Yeah.
Yep,
Okay.
I can see it.
So the general idea is to take some sort of string theory background on some where I play some string theory on some non-compact geometry. So that's what's drawn here. And in this case, the string theory I happen to choose is M theory. And so I have a non-compact manifold, and I can wrap some branes either on cones over some boundary cycles or just over the boundary cycles themselves. And the for simplicity, let's assume this non-compact manifold is just a cone, and the length of the cone I can compactify on it, and the radial directions will over here will become a radial direction in for a field theory that's one higher dimension than the quantum field theory that's engineered at the singularity. And in this dictionary, what we basically have is a defect operator that stretches from the boundary all the way to the quantum field theory. And this thing carries some stress energy because well, in the string theory sense, because this M2 can interact with the M2s and M5s that make up operators in this d-dimensional quantum field theory. And meanwhile, any branes that are just wrapped purely at the boundary would take infinite time in order to interact with the stress energy of the quantum field theory at the singularity. So therefore, these operators would look like topological operators from the point of view of the QFT. And this matches nicely with the current slab, sandwich, or quiche picture, whatever you want to call it, of symmetry TFTs, where I have on the red slab, I have some d-dimensional QFT, some gapped or gapless degrees of freedom, and I have an interval where I have some topological theory, and I have a gapped boundary condition on the other side. So this will be the general picture for the rest of the talk and the rest of the applications. So if you have any questions on this general setup, yeah.
Yeah, sorry, I have a question.
Yeah, sure.
When you say that it takes infinite time for the brane at infinity to interact with the stress tensor, the QFT, it's not very clear to me, because there must be some non-compact direction of the branes along the direction where the QFT leaves. So you're not really separated. There are some directions which are far away, but there must be something of the brane which lives in physical space-time manifold where the QFT lives.
What do I want to say? Well, okay. I guess I maybe another point that might clarify is that when this manifold is a cone, then this QFT is necessarily a scale invariant. So when you see like this topological direction here, I guess what I assume your question is if I'm free to drag this topological operator here, why doesn't that correspond to taking this topological operator from infinity to some finite r? Is that the question?
Well, I don't understand your argument for proving that they are topological. Because you
Well,
said that the stress tensor of the QFT cannot interact with the brane, but they're not really separated because some of the direction of the branes are in common with the direction of the QFT.
They're infinite distance away, so it'd take infinite time for the signal to like if I were to wiggle this M5 in some non-topological fashion, just some it would take infinite time for it to reach the d-dimensional quantum field theory.
But what do you want to wiggle are the direction which are along the dimension of the QFT, not the one at infinity, because the topological operators is given by the direction of the branes which are along the direction where the QFT leaves. So this is what you want to wiggle.
I don't think it matters the direction of the wiggle, but the point of the branes sharing some of the directions of the quantum field theory is perfectly fine, because imagine, like, let's just assume for simplicity they're the same dimension. Okay, I have like two lines, like one line being the quantum field theory, the other one being the topological symmetry operator. They share some direction, let's say, but this distance is infinite. So any type of wiggle I do with this line over here, the topological operator, is going to take an infinite time for the quantum field theory to see it, even though they share, some, like the z coordinate in this example.
Okay.
Okay, yeah, but please, yeah, ask as many questions as you want, yeah. So yeah, so one thing I should say is that because this manifold on the right, which I'm calling X, is non-compact, gravity effectively decouples. G Newton goes as the inverse of the volume of X, and I'm taking that to be infinite. And then, like I said previously, if X is a cone, then this d-dimensional quantum field theory is necessarily scale invariant, because I can just infinitely scale the radial direction of the cone. Okay, so what use is it? Yeah.
Oh, maybe I could just because indeed I think I've also always just been confused about this engineering of the SimTFT from geometric engineering stuff. So the idea is that the M2 and M5 that you've drawn, they are not necessarily topological in the string theory or something like that, but they're so far away from the QFT that they look effectively topological. Is that the argument?
Yeah,
or?
yeah. In this illustration, the M5 is effectively topological, whereas the M2 is non-topological because it intersects the singularity where the QFT lives.
Oh, sorry, the M2 is the black line.
Yeah. Oh, yeah. Yes. So,
Yeah.
yeah. Maybe the illustration could be better, but okay. Yeah.
Okay. And what is, sorry, then, and green is in the string theory, green is
the M5.
uh-huh. Okay. Okay, and then the gravity, so and then why do you need to talk about gravity decoupling then? What's the argument? Like, it seems like you've already got a SimTFT picture engineered and everything before you talk about gravity, or is that?
Well, it's just I mean, it's just an extra technical step to say, because you know, okay, maybe in one hand it's obvious if you have a non-compact manifold, you should have 0, 70 Newton's constant, but you know, I'm just this type of argument you know, shows up if you consider, let's say, initially a compact X and then try to zoom in on some sort of singularity, and that corresponds to taking a low energy limit from a field theory point of view, where G Newton would gradually go to 0. So the point of the Newton's constant statement is to kind of also incorporate these non-compact X's where they're kind of patches of some sort of possibly compact X.
Okay, I see.
So what use is this? Well, the immediate use is that it can be used to determine the symmetries, and in fact, a good chunk of the SimTFT of the d-dimensional QFT. And generically, these operators U, illustrated on the previous slide, are non-invertible. This because this operator U will, roughly speaking, we'll cover some more concrete examples later, will look like an integral of d phi, where d phi is some collection of dynamical fields on the brane. So think of U on gauge field on a D brane. With the integral of the topological action, where I've also included B, which are some additional background fields from the point of view of the string theory brane. An example of this Wess-Zumino term for the case of a D brane in type 2B would look like as follows. I have a sum of Ramon forms, an exponential of F2 minus B2, where F2 is dynamical and B2 and CI are both look like background fields, along with some coupling to the tangent normal bundles.
Sorry, can I ask another question?
Yeah, sure.
It's kind of similar to the previous one, but from a different viewpoint in this case, because I guess that the reason why you only keep the Wess-Zumino term is that because you have in mind that the brane is at infinite distance, so you keep only the terms which are like more relevant at infinite distance, right?
Right, exactly.
But
and
then why
another,
don't you keep
yeah.
why don't you keep marginal couplings, for instance? Say that you have the M2 branes at infinity, so your theory will be a BJM. So it's conformal theory. Why if you put the brane at infinity, you should throw away marginal couplings. They are scale invariant, so
Well, okay, so I think part of the this is also slightly related to one of the open questions that I'll have. But yeah, so for example, like yeah, you have some ABJM having some multiple M2s, then the question is more about how does the field theory on the brane impact the field theory. So it'll you know, the only way it can impact the field theory is through through these topological terms through the same argument as before. Any type of dynamical operators on these branes, you know, would be invisible to the field theory degrees of freedom. So. Okay. Yeah. So yeah, and so one sort of use of this is that this can lead to new field theory developments. So, for example, a kind of nice post-diction of this program that's in a paper with me and collaborators from December 2022 is we constructed for 40 n is equal to 4 theories duality and triality symmetry operators, which closely matched the construction in field theory by Kaidio, Murray, and Zhang. So in some sense, if someone was clever enough with this type of program, they could have discovered those branes before field theorists. But you know, who knows what new type of structures we might uncover from this in application of field theory. Okay, so just a very simple example is 70 Supering Mills. So if I consider M theory on some sort of 7 manifolds times an ADE singularity, where C2 mod gamma ADE, which has as its named an ADE classification, gives rise to a 70 Supering Mills with the corresponding ADE Lie algebra. And this statement, you know, goes back to the 90s. However, the full statement really, considering, you know, what we just discussed, is that M theory on this 11 manifolds gives this full system of a 70 Supering Mills on one end, an 8D sim TFT, and then a boundary condition all the way to the right. And you can think of, we'll see in more detail later, but this boundary condition will determine the global form of the gauge group, because a priori this construction only determines the Lie algebra of the 70 theory. So if one wants to you know, determine what this sim TFT, what this 8D sim TFT is, the strategy would be to reduce the M theory action on partial X, which is given by this this generalized length space of S3 mod gamma ADE, and then keep the topological terms. So for simplicity, we'll let gamma be Z mod n, and then in this case, the second cohomology of the length space is just a Zn. So we can represent such a torsional two-cycle by smooth 2 and 1 cocycle, differential cocycles as follows. I have this alpha 2 and beta 1, such that n alpha 2 is equal to d beta 1, and beta 1 is co-closed. Then I can expand the flux fields of M theory on this torsional two-cycle as follows. So I get some fields that live purely in the length space, which are obviously just alpha 2 and beta 1, and I get some fields that live in the 8 dimensions of the sim TFT, which is this A1, B2, A4, C5. And then what I can do is I can take the action, the kinetic action of M theory, I'm going to ignore the Chern-Simons part of M theory for this discussion. So if I just look at the kinetic term of M theory, which I might now, if you think, oh well, it's it's non-topological, so there should be nothing there. But it turns out when I do this reduction, I end up with the terms that are purely topological. So the terms that involve two derivatives, like this one and this one, that are crossed out, are non-topological because after taking some appropriate Hodge stars, they just look again like kinetic terms for some p-form fields. And then you can reduce this whole action after incorporating this identity of the length space, that this is in our normalization just 1 mod n. And you get an 8D TFT, which is of this BF form. So intuitively speaking, or not intuitively speaking, exactly speaking, I have a B2 background field and a C5 background field, which are background fields for Zn valued one-form symmetry and a Zn valued four-form symmetry. So the one-form symmetry is just the electric symmetry for the SUN gauge, for the 70 SUN gauge theory, and then the four-form symmetry is the magnetic symmetry. So here's kind of the full illustration, where recall red is where the 70 Supring-Mills lives. And blue being the boundary condition, which, in a given M theory compactification, because the manifold is not compact, you have to set some sort of boundary conditions that will well-defined partition function. And so you can have, in general, electric boundary conditions, which B2 is Dirichlet and C5 is Neumann, magnetic boundary conditions, where it's the other way around. And then if I were to, for example, pick the electric boundary condition, then the symmetry operator for the Zn symmetry just looks like e to the I integral C5, where M5 is some submanifold in the M7.
Maybe just
and then the punchline,
a silly question.
Yeah.
Oh, yeah. Sorry to interrupt. I guess maybe this seemed like the right places. Is there like a heuristic or hand wavy or maybe some cute geometric reason why why this theory that you construct when you quotient by this 80, when you put on this space with the 80 singularity, why that only knows the Lie algebra, why you need this choice of bound, you need this choice of boundary condition to also determine the whole gauge group, right? Is there a reason why I should intuitively think that the other, without that I only have like local information about the Lie group? Or
yeah, so if I just think of like an AN singularity, or just like an A1, let's say, the simplest case.
Yeah.
I'm blowing up this singularity, and I'm left with a two sphere. And basically I have, if I were to just reduce the M theory fields on it, it would look like I have some sort of U1 gate symmetry. And if I wrap M2 branes on this sphere, then it looks like I get W bosons corresponding to an SU2. When I start shrinking the sphere to 0 size, and these W bosons become massless. So nothing in that procedure, geometrically speaking, in that blow up picture, singles out an SU2 versus an SU2 mod Z2 gauge group.
Right, you just have three massless bosons that do not.
Right, and another way to see it is that because I have this boundary at infinity, I shouldn't be assigning a partition function to the 70 theory. I should be assigning some sort of vector. This vector is precisely what makes this setup a priori a relative quantum field theory. So there's in string theory literature / it's also used in field theory literature as well. The terminology is known as like a defect group. So this was first thought of in 60 SCFTs, but it equally applies to this gauge theory example, where because the internal geometry of this string theory space is non-compact, I can only define my setup up to a partition vector as opposed to partition function. But, yeah.
See, okay, thank you.
So this is my symmetry operator for the electric symmetry. And then the punchline is that this exponential exactly matches the leading topological action of the M5 brane reduced on, well, sorry for the terminology, an M5 manifold in the 70 spacetime times the torsional 1 cycle in the lens space. And correspondingly, the Wilson line and the fundamental corresponds to an M2 on a 1 manifold in the 70 spacetime times a cone over a torsional cycle. And so the symmetry action of this electric one-form symmetry operator on the Wilson line in the fundamental arises from the Dirac pairing of the M2 and M5 brane because they're electromagnetically dual, tensored with the self-linking of gamma 1 in the lens space. This is kind of how the general paradigm goes for how these action works in these defect operators. Yeah, so the previous example relied on a link pairing which is a perfect pairing that only exists for torsion classes. So I have this perfect pairing in the lens space S3 mod Zn. More generally, if the dimension of the asymptotic boundary is D, then I have a perfect pairing between torsion HK and torsion of HD minus K minus 1, which is all well and great. I can generalize to other dimensions, but what does that have to do with if I am interested in U1 symmetry operators? And I can't dodge the question because I consider the case of X being a conifold, and then partial X is S3 times S2. And if I reduce my M theory fields on S3 times S2, it would look like I have some sort of background fields for U1 symmetries. I have to address this question. And this answer comes from a paper by me, Max, Miriam, and Jonathan from last May, where we proposed that the topological symmetry operators in this case arises from flux branes wrapped on these non-torsion cycles. So flux branes are generalization of flux tubes. These are string theory backgrounds that are, or string theory objects that are in general non-supersymmetric. They've been considered in the literature in the past, and there's some gravitational solutions written for these things. But all you have to really know is that they, from a classical source point of view, instead of having something like D of star F equal to some sort of delta form, we just have star F equal to some sort of delta form where I've included some eta coefficient for later. And so, for example, let's go to type 2B string theory. A flux 4 brane on some M3 times an S2 perfectly pairs with a D3 brane on cone over S3 times a point. In the conifold example of type 2B and a conifold, I'm engineering some sort of 4D theory So this D3 brane is a local operator in the theory. And this, if I just consider the conifold on its own, it's not a very interesting theory, but this is just to get the numbers straight. Then the flux 4 brane is codimension 1 in the field theory. And the symmetry action from before results from composing the intersection pairing of free classes in homology times just the value of the D3 flux measured by the flux 4 brane. So the flux brane, and I should say that the flux brane action, so way back, I mentioned, it's important to consider the Wess-Zumino terms on these branes for the case of symmetry operators for torsion for torsion actions. But in this case of flux branes, the Wess-Zumino term looks like the exterior derivative of some Wess-Zumino term of some D brane. So for example, the flux 4 brane looks like this eta integral D Wess-Zumino of the D3. And you can prove this in supergravity where you input this source term here and this Wess-Zumino term will spit out. And if I look at the leading term of this guy, it'll look like integral of some F5 plus a bunch of more complicated terms. In this form, has some interesting intersection with some recent results just in the field theory literature. So I'm not saying we derive the result beforehand. Symmetry. The word symmetry TFT does not appear anywhere in my collaborator's relevant paper. But what's nice about these two papers is that they actually answered implicitly to me something that I was confused about from the string theory construction, which was if I consider flux 4 brane wrapped on a non-torsion cycle, I get the symmetry operator I want for some U1 action. But if I were to just take a normal DP brane and wrap it on a non-torsion cycle, what does that correspond to? I had no idea, but in both of these papers, there's they consider some operators that are valued in Z, and that nicely matches to this kind of, or answers this kind of mystery I had. And these operators valued in Z is apparently very important if you want to construct sim TFTs involving U1 symmetries. Okay. So now I want to shift gears slightly to now considering X being compact. So notice first that if X is compact, then partial X is trivial. So there's no exact global symmetries to start with. So one might ask, okay, well, how can this machinery be useful? Well, let's consider a case from basically we study at length in a paper from July of M theory on a K3. Now this engineers a 70 n is equal to 1 supergravity theory with a rank 22 gauge group, which I'm going to call G7D. Okay. And you might ask, okay, well, it's, what does the group structure as opposed to just the algebra, what kind of data does that carry? And it carries the data of what are the allowed representations of electric particles and magnetic 3 branes, what representations they can be in. And below the scale of the masses of these particles and the tensions of these branes, the question would be, well, do we recover the expected, approximate global symmetries of just a 70 gauge theory with gauge group G7D? And it turns out, yes, you can make this story precise. And the analog of partial x from the previous examples without gravity is basically what I'm calling x circ, which is just the K3 manifold, but with the singularities excised. So in this illustration here, I've drawn, a cartoon for the K3 where I have a bunch of singularities with some sort of non-abelian Lie algebras associated with each of these singularities, because these singularities are locally always look like ADE singularities. So I have some, G1 algebra, G2 algebra, G3 or G4, G3, whatever. And the point is that if I cut out all these singularities to make this this X circ, then I get basically a non-trivial correlation between the topological operators in this local lens space with this local lens space and so on. And so what I arrive at is that the approximate symmetry operators come from M2 and M5 branes wrapped on H1 of X circ. Considering that there's a perfect pairing between H2 of X and torsion of H2 of X and H1 of X circ, then this implies an interesting relation on the 70 gauge group, which is that well, this general form is expected, has been anticipated in the past, but the non-trivial statement now is that, well, because of this perfect pairing, you should have that. Sorry, let me just explain this form a little bit. So G70 will generally take a form of some simply connected non-abelian Lie algebra modulo some group times a U1 factor, and then modulo some other discrete factor which identifies the abelian guy with the non-abelian guy. Basically, we showed that for all possible K3s, that the Z and Z double prime must conspire such that this Z is the same as the torsion of the center of G70. What this basically means is that the electric particles in the magnetic 3 branes must take values in the same representations. And also I should mention, in a recent paper by Linglin, Gould, and Sabag, they called this a maximally mixed polarization, which is a term I kind of like. So, which also generalizes to cases where you have type 2b on a K3 and you have some non-trivial correlation between the polarizations of the 60 SCFT sectors. Okay. So, and then I'll just mention some stories for another time. Is the generalization of SymTFTs to symmetries, which applies to QFTs with some sort of decoupled sectors. And please see Xingying's nice talk from earlier in this series. I mentioned earlier in the lecture duality and triality symmetries, and also charge conjugation symmetries from an R7 brane, which is basically a new non-supersymmetric brane in type 2b string theory. And also in this same paper where we discuss the R7 brane acting as a conjugation operator, we also mention how other non-SUSY branes can act as symmetry operators in certain QFTs, including some of the recent branes proposed by Kaidi, Omori, Tachikawa, and Yonakura from last year for heterotic string theories. Okay, so let's see how much time left. Okay, so now I want to turn to an application to frozen singularities. So this is based on work in progress with these people written at the top. So now let's return to M theory on this manifold. And if you turn on some sort of monodromy for the C3 field of M theory, which I'm defining as R, equal to some value that's not equal to 0 mod 1, then the gauge algebra mysteriously freezes from G80E to some sort of H labeled by R, the C3 monodromy. So this is a table I just clipped from Tachikawa's 2015 paper, just called Frozen. And he's quoting results based on triples, flexes, and strings from the early 2000s, where if I start off with some sort of ADE group, or specifically D or E type, and I turn on some sort of flux, and so like, for example, if R is equal to 1/2, then for some strange reason, I'm restricted to some sort of smaller rank Lie algebra. And in some cases, I restrict completely to some sort of 0 rank thing where presumably it's some gapped 70 TQFT. And I'll also notice that in general these can be non-simply laced. So if you stare at this table long enough, you'll start to notice some patterns and some strange outliers. So I want to talk about one of these cases. Well, first I mentioned to try to spot an outlier. Notice that so for each of these Lie algebras on top, I can associate a simply connected Lie group, and likewise with the Lie algebras at the bottom. And for the vast majority of cases, the center of the corresponding simply connected Lie group is equal to the center of the guy at the bottom. So for example, the center of E7 is Z2, which matches the center of SO7, which is also Z2. This, because if we try to repeat, so the reason why I mentioned this condition is because if we try to repeat the calculation that I showed earlier in the talk, this C3 appears to not affect the calculation at all, basically because the legs of this background C3 don't have anything to do with the reductions of forms in the action earlier. So it would seem like I get the same BF theory, and if the centers of these things are the same, then that seems perfectly okay. But some outliers are basically this guy and this guy, where the center of this SP is Z2, and the center of this thing is in general has 4 elements, whereas the center of E8 is obviously trivial, and the center of SU2 is Z2, so there's some sort of mismatch. So the question is, what's going on? So this is what I said. When gamma is E8 with 1/4 flux, so going back to the table, okay, I had 1/4 flux there, or 3/4 alternatively. Then it appears that we have no 1-form electric or 4-form magnetic symmetries to even speak about, which seems fairly weird. It seemed like we have kind of like a trivial polarization in a way. And so our proposal in the paper is that, or in the work in progress, is that the 8D sim TFT action, at least the one that encodes the usual mixed anomaly between the 1-form electric and the 4-form magnetic symmetry, is trivial. Now this is obvious in the duality frame of M theory, because the second cohomology of the lens space is trivial. But we've confirmed this in other duality frames that this really seems to hold. And there's actually a fairly simple resolution to this, is that okay, if one assumes that the one form symmetry and the four form symmetry are not symmetries of the 7D theory, then we're free to add a counter term to the theory, which explicitly breaks these symmetries. And such a counter term, if you were to try to lift it to 8D, would exactly cancel the naive sim TFT that you get from the gauge theory in the first place. So adding this counter term in some sense adds up with the naive sim TFT to give a result of just 0. And adding such a term then renders the SU2 fundamental Wilson and 't Hooft defects inconsistent. And the reason for this is that if I have a fundamental Wilson line, I can think of this as turning on some sort of source for the B5, or sorry, C5. And then the point is that if I, what am I gonna say? Yeah, and then if I do some sort of background gauge transformation for the electric symmetry, my partition function won't be invariant. So it's just the usual statement of an anomaly, but I don't get this cancellation, but I don't get help from the sim TFT, which normally, inflows from anomalous transformations of the partition function. So basically, I would conclude that I don't have, I can't even speak about fundamental Wilson or 't Hooft defects in the theory. And I could also mention what this looks like in other duality frames, so that maybe seems less mysterious. But yeah. Okay. So so some open questions from this program of symmetry operation branes is, well, one is a practical one, which is how detailed can we understand the categorical symmetry structure of a given QFT from string theory? So there's some interesting partial results in this direction. I mean, in particular, a lot of the non-invertible fusions that we calculate in these papers is some sort of sign of a categorical symmetry, especially because what results in these fusion algebras usually ends up being things like condensation defects for other higher form symmetries. But it'd be nice to have a better systematic understanding of this. One sort of conceptual question is, what happens to branes wrapped on partial X that wrap finite volume cycles? So what I've done this entire talk is, basically this entire talk, I've assumed that all the cycles in partial X are infinite volume, which is not super surprising because partial X is infinite volume. But I can have cases, for example, like the asymptotic boundary of Taub-Knot, where S1 stays finite size, even though partial X has infinite volume. So how do I interpret these branes there? It seems like I have, in some sense, sort of dynamical topological symmetry operator, which seems kind of contradictory. And another application to pure field theory would be that to non-commutative field theories. So string theory, handles or gives a nice way to construct non-commutative field theories, usually by just the easiest way being to turn on a B2 field, B2 background fields on a stack of D branes. And the question would be, what can you learn about the generalized symmetries of non-commutative field theories, and do they even correspond to, what's the notion of submanifolds do you have in these cases? And then the last question is related to I think Andrea's question earlier, which is when I fuse these branes at infinity, there's in some sense a choice I can make. Either they fuse in such a way that they don't actually that they don't actually touch, like they just touch in the 4D spacetime, but they don't touch in the 10D or 11D spacetime. And in that case, I don't end up with new massless string states, or like as he was saying, the like an ABJM. But is there some sort of deformation of these fusion relations where I get these new massless string states, and do they somehow talk to the field theory in any way? Intuitively, I didn't think so, but I'm not 100% certain on this question. Yeah, and then I just want to end with thanking all various collaborators on some of these papers. I did a very bad job citing other people and citing my own work throughout. So yeah, so just thank you there. And then thank you all for listening.
All right. Thanks a lot, Ethan. So I guess the first things first is if anybody has questions. Otherwise, I got two, but I'll see if anybody else has got one first.
Yes, about this idea of this flux branes. Can you use this idea to engineer symmetry operators for non-abelian continuous symmetries?
So that's a good question. I'm not sure I'm at liberty to speak to go too much detail into an answer. But I would say, okay, so I would say the issue with the yeah, I'd say it's not obvious just from the flux brane picture how to handle non-abelian symmetries. It would seem like you need some extra ingredients into the game for sure.
But why like the naive thing that I would do to like take a stack of flux branes doesn't work?
No, I mean, yeah. So I mean, if you take like a stack of flux branes, then it would seem like you have a some sort of non-abelian topological theory living on these topological operators.
Right.
But the action that it has on the defect operators still appears as a U1 action. So it'll be a U1, and then like well, it's kind of familiar to like a lot of non-invertible examples where it'll have an invertible piece and then some non-invertible mess in addition to it. So it would kind of look like one of those.
And do you have like other ideas or proposal for how to engineer, or whether it's possible or not? Maybe it could be that it's not possible to construct symmetry operator for continuous non-abelian symmetries from branes. I don't know, or
yeah, I mean,
like take SU4 SU4R symmetry in n equal to 4, again, like the simplest example.
So I will say, yeah, I mean, I will say like a general one thing I was thinking about adding to the open questions when you say R symmetries is, like just isometries in general. So even when the R symmetry is, abelian, it's not clear that there should be any brane corresponding to this because this corresponds to some sort of geometric isometry. So if you were to construct the brane, it would look like some sort of very singular 11D or 10D geometry as opposed to some sort of brane. Yeah, so I mean, I suspect this is also part of the reason why earlier in the lecture I said like these branes at infinity construct part of the SymTFT, but it would certainly miss some of it, like for example anything that interacts with these R symmetries. Yeah.
Yeah, because actually I never understood if there is and why, if there is a principle telling you that any kind of symmetry in any QFT engineered by string theory should come from some brane. It seems that for finite symmetries, it's always the case. Now you're telling me that for U1 symmetry is also the case, but many symmetries, even like in holography, just come from isometries of the compact space. And it's not clear to me whether they should correspond to some, they should give rise to some topological operator coming from some brane or not. And this would, if there is a
I'd say the
principle.
correspondence. Yeah, I mean, I totally agree. The correspondence is not one-to-one. It's like the space topological symmetry operators in the QFT is more general, totally. Now it could happen that you get lucky with some sort of duality transformation where something that looks geometric in one frame looks like a brane in another.
Oh yeah, that's right. Yes.
But one may not always be that lucky. I mean, I just think the general answer is that it doesn't always have to be some sort of brane, but could be some sort of localized mess. So for example, in holography, if you want to talk about, like I have some topological symmetry operator corresponding to the R symmetry on the field theory, which I'm free to talk about. What's the holographic dual of that? I would suspect it's some sort of weird sum over topologies where I'm doing some sort of twists by the R symmetry, by the isometry in some way. Yeah. The reason why why I say that is that if I have, let's say, like a parity symmetry in the CFT, what does that lift to in the bulk? In the bulk, I know that to mean that, oh, well, I should, in my sum over topologies, I should include non-orientable manifolds, for example.
Well, that's because of space-time symmetry. But your symmetry is internal.
Well, no, but I mean, I was informing the R symmetry guess. The R symmetry is kind of in between because it's internal in the boundary, but space-time in the bulk.
Good.
One of my questions was, I guess, partially scooped. So let me switch to the other one, which is your last bullet point of your last slide. You're talking about deformations of things. Do you mean specifically like deformations of symmetry structures? And do you explicitly mean in what do you specifically mean? Like yeah.
No, yeah. So I would, deformations, some sort of symmetry structure. Is that, the question is that physical in the QFT? So the deformation I have in mind is some sort of branes, ad infinity that overlap some sort of at the same manifold in the 4D spacetime, but and also, let's say even occupy the same homology class even, but the actual form of these branes in terms of actual cycles do not overlap, or only intersect at one point or something like that. You can consider deformation where now you take these branes to be perfectly coincident, and then you get some new open string sector. So like a some non-abelian gauge theory now living in the brane, or some CFT or something. Does that deformation in the string theory correspond to a physical deformation of the symmetry structure in the QFT? Is kind of the question.
Right.
So
I just
I don't know
asked
if that
because
deformation is invisible to the QFT, but it could be, but I don't know.
Yeah, I was just asking in what context you meant, because I mean, there's the famous statement of Ocneanu rigidity, right? Where you basically can't continuously deform fusion categories. So I didn't know if, but that, I think that involves the fact that it has only finitely many simple objects and things like that. So I didn't know if maybe you were considering in the continuous case, or you weren't necessarily considering continuous deformations at the level of the symmetry
Sure,
category.
I think this would fall outside of that, because this deformation of like, oh, the branes aren't coincident and are coincident it seems kind of discrete, like it's either they are or they aren't.
Right. It would be a
So
discontinuous jump when they become
yeah,
coincident or something. Right.
yeah. So yeah, could be interesting to think about.
Okay. Are there any other questions? No, maybe. All right. Hearing and seeing none.
All right.
Yeah. Let's thank Ethan again and see everybody in 2 weeks, I guess.